All right, so if we want to find the electric field a certain distance above or below a sheet of charge, we can use Gauss's law. So let's write out our sheet. Kind of looks like that, right? And this sheet is of some uniform charge density, sigma, q over the area, right? Whatever area, whatever charge, it doesn't matter. The ratio of those two is constant, sigma. Again, sigma for the surface charge density, that's the variable we typically use, right? Sigma for surface, S for surface, okay? All right, so what Gaussian object or what shape of Gaussian surface will give us the easiest route to find the electric field, a distance above and below? Well, a circle won't necessarily do. We need some type of object where we have equal distances above and below, and a face with the electric flux to be maximized. For instance, a cylinder fits that criteria. Okay? And this cylinder should be the same height above as below. So I'm going to call that H and that H as well. Okay? So again, this is our Gaussian surface. Our Gaussian pillbox is what some textbooks say. Gaussian cylinder, whichever. Which surface of that Gaussian cylinder will have a non-zero electric flux? Well, the surface on top has the area vector normal to the surface. That's going up. The one on the bottom goes down. And the sides, well, go outwards. Right? This sheet of charge has an electric field that's going up, that's creating a field going up and going down. It's some sheet of some plus charge. So this is why we have both heights, both top and bottom of this surface, the same distance, right? Because we're estimating the electric field at this height or at that position. And so it's creating two fields on top and bottom, so we have to have effectively two pillboxes, right? And so that's the same height h from the plane as it is on the bottom, okay? So Gauss's law, closed integral of E dot dA is equal to the total charge enclosed over epsilon naught, right? And by the way, do not forget this inside, right? This is essential to Gauss's law. It does not make sense if you just have some ordinary charge. It has to be the charge enclosed of your Gaussian surface, right? The charge inside there. So do not forget this inside. Okay? On the left side, we need the electric field to be constant, right? Hopefully it is. Hopefully we've chosen our Gaussian surface to be symmetric such that we can pull out our electric field, right? And we have. So now we have the closed integral of dA, right? And by the way, if we evaluate that dot product, we should have a cosine. And in both cases, the electric field and the area vectors are parallel. So thus we have a cosine of 0. Okay. All right, I should write, actually, let me hold off on that for one step. Okay, so our charge enclosed, we can rewrite, well, we have a relationship with sigma and q. So solving that equation for q, we get sigma times some area. So we'll just keep that as a general area for now. Okay, back to the left side. The electric field is constant. We have two surfaces that have non-zero electric fluxes, right? This top surface and the bottom surface, right? That bottom face. So that means we have two terms on the left side here. This closed integral is of the entire surface that has some flux. So really we have integral, I'll say top, or rather, let's do it like this. Area of top. No. Plus area times the integral dA for the bottom. Okay, two terms. So electric field still constant. What's the area of that top face? Well, that top face is really just a circle, right? Because we've chosen a right circular cylinder, so that area is just, well, pi r squared. Plus the second term, E, the same thing for the bottom, because this is a symmetric cylinder. And the right side, sigma. Now this area, what's the area that has the actual charge inside this Gaussian surface? Well, that's that area right there. That's the same area as the top and bottom faces. So, pi r squared, right? Yes, you could keep each of those areas as just A. That's okay, right? That's completely fine. You'll see they'll cancel out because we really have two E. Those go away. Equals sigma over epsilon naught. And so the electric field is simply sigma over 2E. And that's it, right? If you want to plug in for sigma, right? Now to put this in terms of Q, you can. Let's see. Sigma is really Q over 2 epsilon naught times some area. And looking at the dimensions or the units, we have Q is in coulombs, epsilon naught on the bottom, and area is in units of meters squared. So this still holds for Coulomb's law, right? So we're good. So for a plane of charge, plane of uniform charge, this is the electric field expression at a distance h above it. You might notice that it does not depend on h, right? So there you go.